Guys, this is Mobeen. We're talking about pulmonology. We're going to take up this first point. What we say is that in the environment, so let's say this is a person, this Joe person is present in the environment. The environment, we say, has the pressure of 760 millimeter of mercury at room temperature, 37 degrees centigrades, and at the sea level. So that's a given. Question is, what does this mean? So let's very quickly understand that. In this environment around us, there are two gases that are primarily making this environment up, this air up. These two gases are oxygen and nitrogen. Oxygen and nitrogen. I will write nitrogen as N from now on. So oxygen and nitrogen. Oxygen is 21%. This is the concentration of the oxygen in the environment around us, about 21%. Nitrogen and other minor gases make up the remaining 79%. What are the minor gases? Of course, the carbon dioxide is coming on, there is argon, there is helium, there are other small minor things, but primarily it is nitrogen. So for our discussion, we'll say 21% oxygen, 79% nitrogen. Okay, so that is a concentration part. What is their relationship to the pressure? What is the pressure of a gas? Look, we did that in the physics as well. What happens is gas is really what? Molecules. These molecules are bouncing around and they're running around, and what do? When they hit some surface, they keep going straight. They have kinetic energy. They keep going straight, and when they hit some surface, they bounce off. Or they hit each other and they bounce off. So if you take a box and you put gas in there, or air, let's assume this room is a box and there is air in it, gases are oxygen and nitrogen are just running around their molecules and they're bouncing they keep going straight till they bounce something, then they deflect from there and so on. Okay. So when the gas molecule hits a surface, it exerts energy, it expends energy there. It spends energy, it causes pressure. So pressure is actually a mechanical effect of the molecule hitting a surface. Got it? Why do I care that I want to explain that? Here is why. If the pressure is because of the mechanical push by the molecule, then a gas with the more molecules will have more pressure, and a gas with less molecules will have less pressure. In the air, I'm not talking about in the fluid, I'm talking about in the air, atmosphere, sea level. And so here is the key point, clinically important point, keep this in mind. The pressure is equal to the concentration. So what does that mean? What that means is, if oxygen is 21% of 760, then oxygen's pressure is also 21% of 760. It's simple, because it is the mechanical bouncing of the molecules. So if the molecules are 21% of some pressure, then some concentration, then their pressure is going to be the same percentage. Okay, so let's do the math here. 21% of 760 is about 159 millimeter of mercury pressure. So in the air, oxygen exerts, around me right now at the sea level, we are in California, so this is sea level. Around me at the sea level, the pressure of oxygen is 159 millimeter of mercury. Okay, how about nitrogen? All the rest is nitrogen. So all the rest, so 760, so if you take 160 out of 760, remaining 600 millimeter of mercury pressure is exerted by nitrogen. No problem here, right? Right? This much is clear. Got it. Now, one more thing before we start working on the body. Water vapors. What is their effect? Look, let's say we take a pot. Let's say this is a pot. I actually have a pot here to show you as an example. So let's say this is a pot that contains water, right? So I'll have something here. this is a pot with some water. So look, there is gas in this pot as well, there is air here as well, but near the surface of this pot, where the water surface is, water molecules are constantly escaping. That is why if you leave the pot out in the air, the water would slowly evaporate. So water molecules are escaping, they are evaporating. So do you think that the air, the oxygen and nitrogen is near the surface of the pot, near the surface of the water, the amount of air and nitrogen is the same as here? I hope you said no. That is the important thing, and I can explain why not. Look, water is evaporating. So there is some percentage in this area right above the water, there is some percentage of the space that is taken up by water vapors. So let's say if we draw a diagram here and we said this was the atmosphere, and in this atmosphere 21% was oxygen, and the rest of, I'm going to make it with green, it would look little lighter, but that is a point. I don't want you to focus too much on nitrogen. So this is the 79% nitrogen. So the major pressure here is by the nitrogen, but 21% of oxygen. That is important for us. Here what's happening, there is water involved as well. So let's say I tell you that the temperature is such over here that the water is exerting 30 millimeter of mercury pressure. I just made up a number. So now let's see, if water is making 30 millimeter of mercury pressure, then what we need to do is, should we subtract water from oxygen? So oxygen has 159 millimeter mercury pressure, right? Shall we say that water has 30? So I'll say pressure of water equals 30 millimeters of mercury. Shall we take this and remove it from 159? No, it doesn't make sense, because this gas is combined gas. How can you just say water, say, you know what, I only want oxygen to get out, I only want oxygen to give me away? That's not going to happen. How about we say that water would take up space that is taken up by nitrogen? So now what is water saying? Water is saying, I only want to take space from nitrogen. That's also not going to happen. Water is going to push them both out together. What does that mean? If I increase the water in here, if I pour more water here, air will exit this equally in the equal percentage, oxygen and nitrogen. So to calculate the percentage of pressures and concentrations right above the water surface, we need to first take this pressure and reduce that from the 760. Okay, so let's do that. So 760 minus 30. 760 minus 30 equals 730. So now right above the surface of the water, the atmospheric pressure has fallen to 730 because of the gases. Total pressure is still 760. Where is the rest of the pressure coming from? From the water. Total is still 760. Okay. So if it is 730 millimeter of mercury, then what do you think is oxygen's pressure and nitrogen's pressure? Do you think that the oxygen concentration changed? No, we just established no. Nitrogen's concentration changed? No. So if the concentration is the same, then you take this concentration and multiply with this, and you have the new concentrations. So 20% of 730, that is what you are getting at. So I'll do the math just so that we both are on the same. So 730 multiplied by 0.21, 21%, is 153.3%. So let's just call it 153. So now oxygen, here if I draw this thing, now oxygen is how much? 153 millimeters of mercury, and of course the rest is nitrogen. So this is an important concept. Why is this important? This is what happens inside our lungs. As soon as the air enters our mouth and nose, right from there the wet surfaces start contributing the water vapors. And water vapor at our body temperature, what is our normal body temperature? 37 degrees centigrade. At 37 degrees centigrade, the water vapor exert 47 millimeter of mercury pressure. 47 millimeter of mercury pressure. Never forget that for your whole practicing career. 47 millimeter of mercury pressure at 37 degrees centigrade. If you bring water temperature up to 100 degrees centigrade, then the water would exert 760 millimeter of mercury pressure. So we are not asking you to boil the person, we are asking about 37 degrees centigrade normal temperature. Okay, so water, I'll write it down over here. Water at 37 degrees centigrade sea level exerts 47 millimeter of mercury pressure. Okay, got it. So then one more thing, students get confused with this one, and this is actually very simple. This come to me and they say, you know what about we read PO2, then we see PaO2, then we see P small aO2. What are the differences in those? So first let's explain the P, partial pressure. Why do we call it partial pressure? It's very simple. Look, there are two gases in here, right? The two gases are their combined pressure. In this case, actually, let me add water as well. There is water as well. So 30 by water, 153 by oxygen, and all the rest is nitrogen, right? So they all combined make 760. So can I say that the oxygen's pressure out of 760 is its part? So that is why the word partial pressure. So whenever you're talking about environment, the pressure, the term that you would use it, you'll say pressure of oxygen or partial pressure of oxygen. So you'll write PO2, or partial pressure of carbon dioxide, PCO2, or partial pressure of nitrogen, PN, and partial pressure of water, PH2O. Okay, got it. So that is a partial pressure. We now understand why we call it partial. How about PaO2? That is the pressure, partial pressure of a thing, that may be water or that may be oxygen or carbon dioxide, inside the alveolus. So the capital A defines the alveolus. How about P tiny a, small aO2? That is arterial. So that is arterial blood gases, ABGs. You do that in the hospital all the time. So ABGs, these will be written with the small a. Got it? So we'll go there and we'll explain that in a second, but just know this is what we mean. Now as we going to work on this diagram and see what happens when we take the gas in, please realize that there is inhalation and exhalation. So let's start the inhalation process. The person here, Joe, inhaled the atmospheric gas at sea level, 37 degrees centigrade body temperature. So what is the concentration? He inhaled 160 millimeter of mercury pressure for oxygen, and the rest is nitrogen. Total pressure 760 millimeter of mercury. Same thing as here. As soon as the air strikes the surfaces are evaporating the water. So imagine our mucosal surfaces inside, and they are just having vapors coming out of them. What are these vapors? Water vapors. So vapors everywhere. So these are remember these surfaces are all wet. So because these are all wet, they are giving off water vapors. At 37 degrees centigrade, what is the pressure of the water vapor? 47 millimeter of mercury. So let's say PH2O is 47 millimeters of mercury. Now please remember one rule. Pressure, total pressure cannot exceed the atmospheric pressure. if atmospheric pressure is 760, then all pressures combined have to fit in that 760. So water has taken 47. What is left now? Out of 760, if it was 50, we are left with 710. So really 713 is left. Now if the 713 is left, let me make that structure here. Water has taken 47. That is water. Total is still 760. That is this total. How about oxygen? What is the percentage of oxygen? 21%. Of what? 760? Not anymore. Why not? Because water has taken 47. What is left? 713. This is 713. Okay, so the remaining pressure left to be used by gases is 713 millimeter. Now oxygen is 21% of this 713 now. So what would that be? 713 multiplied by 0.21, 21%, 0.21. So 149.73, so about 150. So I'm going to say oxygen here is 150 millimeter of mercury is oxygen's pressure. And the rest is nitrogen. What is the rest? Nitrogen. You subtract these two pressures and rest is nitrogen. I don't want to do that math here. I don't want to waste your time. So that is the pressure. Important thing is notice that oxygen has dropped 10 millimeter of mercury pressure. Why is the pressure going to be important? We'll see that pressure is going to be important for the gaseous exchange. So keep this in mind. Is there any carbon dioxide in here yet? No. Why? Because we are still in the anatomical dead space. Imagine now that you have reached the respiratory area. What is the respiratory area? Respiratory zone. That is the zone where there is the respiratory bronchiole, alveolar duct, alveolar sac and alveoli. We have done that in the histology of it. So we are in the respiratory zone where the exchange can occur. So imagine, stand here for a second. Let's say I cut it here. Stand at the door of the respiratory zone. What is the concentration of oxygen there? 150. Look in, peek in, check what's going on here. Before we decide, just like parrots that, well, the pressure would change. Look in, what's happening is, the blood that is coming in, venous blood, what is the venous blood bringing back? Guys, venous blood is bringing back waste products. One of the waste product is carbon dioxide. So it has carbon dioxide here. And what is less in the venous blood? What is gone from the venous blood or reduced in the venous blood compared to arterial blood? Oxygen. Arterial blood had more oxygen, tissues have eaten it. Tissues ate the oxygen and gave back the carbon dioxide. Carbon dioxide is more here, oxygen is less here, more here. Got it? So carbon dioxide is here. This carbon dioxide that is sitting here is going to move into the alveolus. This is a really important concept to understand. Why? Well, you say, well, gaseous exchange occurs and oxygen goes that way to the arteries and carbon dioxide comes back. We know that. No, that is not it. We have to say it this way. Carbon dioxide comes back into the alveolus. Okay? So if carbon dioxide comes into the alveolus before this gas are breathing in, before that reaches here, why is that magic important? Here is why. Look, I'm going to use that over here. Here, again, total pressure here should remain 760, right? 47 is already taken up by water, right? So this was water, it took up 47. Now another 40 is taken up by carbon dioxide. Carbon dioxide jumped in and said, I want to have some pressure too, and it had 40 millimeter of mercury pressure. That is carbon dioxide. We are talking alveolus now. We know there is water, so 47 went to water. Carbon dioxide is 40. Now we are left with the rest. So question to you, this is why I said this is important. Can carbon dioxide say that I am going to displace oxygen? Yes. Now the question is, why yes? Why yes? So I've seen students saying, well, you know what, carbon dioxide comes in, oxygen goes out. Well, if carbon dioxide comes in, why does nitrogen not go out? Right? So here are a couple of things to remember. Number one, in the alveolus, between the alveolus and the blood, there is a concentration difference in the gases. Nitrogen is in equal concentrations, so it doesn't matter for nitrogen. The only thing left is oxygen and carbon dioxide. That is one. Second, when we eat some food, let's say carbohydrate, if I eat carbohydrate, so I take carb, and if I use 10 oxygens to digest this carb, then I produce 10 carbon dioxide as well. Carbon dioxide are produced. Okay. If I eat fats, if I take 10 oxygen, I actually produce 8 or actually 7. I produce 7 carbon dioxide. So you look at me and you say, what is that magic? Why would that happen? Okay, so let me tell you this. Remember, in the biochemistry you may have read that if you have glucoses or carbs and you have fats or fatty acids, remember the fatty acids are even chained carbon substances. Glucose, when it reaches to pyruvate, and before the formation of pyruvate, it would release carbon dioxide. Then is a Krebs cycle, that is also going to release carbon dioxide. However, fats actually contribute directly under the pyruvate. So this carbon dioxide is not generated. So what we are left with is, in case of fats, only this carbon dioxide is produced, this is not produced. But oxygen utility in FAD and FADH2 and those, oxygen utilization is the same in the electron chain. So oxygen is still the same, but carbon dioxide produced is different. What you can say is that if you take glucose, then more waste products are produced as compared to fats. Now come back here with this concept. If I am eating carbs all the time and my venous blood brought back, let's say it brought back 40 millimeters of mercury carbon dioxide pressure. It brought enough carbon dioxide concentration back that it created 40 millimeter of mercury pressure. So that means 40 milliliter of carbon dioxide. Let's just use it that way. If there is 40 carbon dioxide and I'm eating carb, then how much oxygen is needed to produce this 40 carbon dioxide? 40 oxygen. So 40 oxygen will have to move into the blood so that this can be equated. So for USMLE, use 1, the ratio of 1. Imagine the person always eat carbs for USMLE. So for 1 carbon dioxide produced, there is 1 oxygen used. For clinical terms, we use 0.8. That is a mixture of carb and fats, and we say, well, for each carbon dioxide produced, for each oxygen consumed, there is 0.8 carbon dioxide produced. If somebody is only on fats, then 7. Okay, so we got that. Back here, we've gotten the air. Now let the air come in. This air came in, 150 millimeter of mercury oxygen pressure came in. There was already carbon dioxide 40 millimeter of mercury. We are going to now do something to this oxygen, that the total pressure has to remain 760. So now what we need to do is we need to subtract further pressure from oxygen. So what is that formula? This is the formula that you would see in the USMLE. The formula is this. Look, it is actually very simple. PA alveolar CO2, sorry, not CO2, O2 equals pressure atmospheric, which will be 760, subtract the pressure of water, which we have been doing, so 47, right? So 760 millimeter of mercury minus 47 millimeters of mercury, multiply it with the fraction of oxygen, incoming oxygen. So what is the incoming oxygen's fraction? 21%. 21% here, 21% here, 21%. It's 21% everywhere. So 0.21 is 21%, right? 21 divided by 100, 21%, minus the carbon dioxide PaCO2 divided by this gas coefficient. So what is this gas's ratio, or the carbon dioxide to oxygen usage ratio? We will use 1. Let's call it R. In our case, we'll use it as 1. You can use it as 0.8 or 0.7 depending upon what is your setting. 0.8 in clinical terms. So let's measure this now. So 760 minus water, we are left with 713. Multiplied by 0.21, we are left with 149. So this is the 0.21. Minus PaCO2, which is what? Here 40 divided by 1 is 40. So minus 40 here. So we are left with 109 millimeters of mercury. So the pressure here now of oxygen is 109 millimeters of mercury. So can I say something now? Total pressure has to be 760. Oxygen's pressure we just determined 109. Carbon dioxide's pressure is 40. Water's pressure is 47. Rest is nitrogen, right? So 47 water, 40 this. We just calculated oxygen 109, and what is rest? That is nitrogen. Now my question to you, why do we do this 40 thingy and have this formula and then do this? Look guys, this is why I said exhaling is also important. This gas is going to get out as well during the exhalation. We can trap that gas and try to understand what was the alveolar air concentration or composition. In the books you would read a term that says end tidal volume or end tidal air. What does that mean? That last air is coming from alveoli. If I keep exhaling, now I'm getting the functional residual expiratory reserved volume is also coming out. Where is it coming out from? From the alveoli. When I start exhaling, first air that goes out is from the anatomical dead space. Do we want to use that? No, because the concentration in there is the same as atmosphere. But as the air comes out from the alveoli, end of the tidal exhaling, that would be the alveolar air. Now here is the question. When you are exhaling, you think that the oxygen that would come out and the carbon dioxide pressure will be 109 and 40? Will you get here 109 and 40? No. Why not? Look, as the gas starts moving out of the alveolus, it's going to mix with this gas or all the gas in the dead spaces, physiological or anatomical. All the dead space gases are going to mix with this. So in the dead space, is oxygen more? Yes. How much more? 150. What is the oxygen here? 109. When this 109 volume passes through here, some of the 150 would mix with it. So oxygen level will go up because there is more oxygen sitting in the dead space and that would mix with this less oxygen. Oxygen level will go up. How about carbon dioxide level? There is more carbon dioxide here. But as the gas moves during the exhalation, it mixes with the dead space air. Does the dead space gases, does it have carbon dioxide? No. So no carbon dioxide in this, more carbon dioxide in here. When you mix them, will you get lower carbon dioxide overall? Yes. So exhaling will not actually give you this end tidal air, will bring you something like oxygen. Let's say I'm doing exhalation here. Exhale will bring, let's say, pressure of oxygen. Look, I'm not saying PaO2 now. Why? Because this gas has come out now, but this is outwards. This gas, when it was coming in, the oxygen should be called PiO2, inhaling oxygen, PiO2, all inwards. This is outwards. P outward O2 is going to be more than 110. It's going to be probably 123, 125 millimeter of mercury. Why? Because it mixed with the other gases on the way. How about P outward CO2? Here it was 40. While going out, it got mixed with no carbon dioxide, so carbon dioxide concentration reduced. So maybe from 40 it went down to 30 or something. We should actually do a math to figure out what should be these, but that is how it goes. Guys, so just one correction. I called this respiratory quotient, I think. It is respiratory exchange ratio. Respiratory exchange ratio. So keep that in mind and please correct that. Okay, so back here. Now when we have the gases that are here, what will happen at this area? So really not much of a problem here. We'll have gases that will be diffusing from the alveolus to the blood or from the blood to the alveolus. The question is, why will they diffuse? These will diffuse because of the pressure gradient difference. So you say, aha, I got you, Dr. Mobeen. Over here we've gotten the air medium and over here we've gotten the fluid medium. Why are you treating them the same? So guys, please remember this here. For the gases that concern us, oxygen and carbon dioxide, they are very fluid dissolvable, they're very water soluble. Although keep this in mind that carbon dioxide is 20 times more soluble than oxygen. That is the solubility. Carbon dioxide is 20 times more soluble than the oxygen. Oxygen is 20 times less soluble. Why does that matter? Here is why it matters. Imagine this room is filled with water and I jump in and I say, let me in, and water hates me and says, get out of here right now, go away. I will exert pressure. I'm not taken up by the water, I'm not calmed down, so I'm bouncing around and I'm trying to get out. That is the pressure exerted. So any gas that is not dissolved in the water or that is less dissolved in the water will create pressure in the water. It would run around the molecules. On the other hand, if a gas that dissolves more in the water, for example carbon dioxide 20 times more dissolving, that would reduce the pressure, because now it is hugging the water molecules and just sitting there, not running around, not bouncing, not creating pressure. So please remember this, a gas that dissolves more in the water produces less pressure. So here we also have a pressure of the gas in the fluid. What does that mean? I've seen students becoming so confused. Look, there is RBC here, right? So this is an RBC. Why is this RBC almost blocking the lumen? Look, RBC is about 8 micrometer in diameter. The lumen of the capillary is about 5 micrometer. So RBC has to squeeze through this. So it is touching the surface. That actually allows the gases to exchange faster with the RBC instead of going into the plasma and then going into the RBC. Anyways, the pressure that is exerted here in the fluid, this pressure is not just dependent, please remember this, it's not just dependent on the concentration, it is also dependent on the solubility in the fluid. And the pressure of oxygen or pressure of carbon dioxide in the blood is actually the molecules that are in the blood, not on the hemoglobin in the RBC. So when we say partial pressure of carbon dioxide in the blood, that is the dissolved carbon dioxide sitting, and the carbon dioxide which is not dissolved. These guys collectively create a pressure. Same for the oxygen. So that's one. Second, because carbon dioxide and oxygen are very lipid soluble, for them the lipid membrane of the cells are actually nothing. They very easily cross them. They cross water as well, and they cross, see, we just talked about the water solubility, and they cross the cell membranes too. So here is the water, this is the water layer, so they'll cross the water layer. Then what will we get next? Epithelial cells, they would cross the cell membranes of the epithelial cells. Then what do, so they'll pass through the cell. Then what do we got? We got a very thin layer of interstitium. They'll pass through that, if it is oxygen, let's say. Then it would pass the, there was a basement membrane as well, right? So don't forget that there is this basement membrane. And then endothelium also has a basement membrane. Then endothelial cells will be coming next. And so fluid layer, epithelial cells, basement membrane of epithelium, interstitium of the lung, basement membrane of the endothelium, and then either in the RBC or here. Now if the pressure is less here and more here, which is the case for oxygen, oxygen's pressure is 100 here, PaO2 is 100 here, and or 110, we did the calculation, and the PaO2 here is normally about 40. So oxygen here is about 40. And we take the oxygen at the beginning of the capillary, not at the end of the capillary. So I should make that here. PO2 here is 40 millimeter of mercury. So what would happen? 40 here, 100 here, the gas will move from the alveolus to the blood. Carbon dioxide, on the other hand, is 47 here in the blood and about 40 here, or actually in the beginning it was 0, right? When the gas came in. So it starts diffusing out. How much does it go out? 40. And so that is what happens. So PaCO2 is 40. PCO2 is 47. How about P now small a CO2 and P small a O2? Ideally it should be the same, right? So if it is 47 here, P CO2, when the carbon dioxide comes in, the pressure is higher, then carbon dioxide moves out and the pressure that comes out is lesser, so about 40 millimeter of mercury. Then it will go back and bring more carbon dioxide. Oxygen comes in and it is less, 40 millimeter. Then more oxygen equilibrates from the alveolus, 100 equilibrates. So when it comes out, it should be 100 millimeter of mercury. Although this is slightly different. Instead of 100, it is 95, and it is, instead of 40, it is 42, 43. Why? Because there is dead space in the lungs. That dead space collectively, when all of the blood is collected back, that dead space where the oxygen exchange did not happen, that when accounts in, then the total is, instead of 100, it actually is PaO2 is usually 95 millimeter of mercury. So what happened? Dead space happened. Got it. So I hope that this is clear. Now let's talk about what are the factors that affect the carbon dioxide and oxygen diffusions. So let's look at the carbon dioxide first. It is easier and we can get done quickly here. Carbon dioxide, there are two factors that affect it. One is the metabolic rate. So if you see here, carbon dioxide is directly proportional to, pressure of the carbon dioxide is directly proportional to metabolic rate and inversely proportional to ventilation. What does that mean? If I stand here and for some reason my metabolic rate increases, then the carbon dioxide production will increase, right? It's part of the respiratory burst and respiratory cycle. And if I start ventilating more, what will I do? I'll wash away, I'll wash out the carbon dioxide that is sitting here, right? When I'll wash out the carbon dioxide, then the carbon dioxide pressure in the alveolus would drop. So how much, what does that mean? Look, normally the PaCO2 range is 35 to 45. So if it is lesser than 35, for example, I'm standing here and I'm breathing, I'm hyperventilating. If it drops below 35, then by definition we call it the person is hyperventilating. If it goes above 45, then by definition we say that the person is hypoventilating. Okay, so if it is more than 45, then it is hypoventilation. What does that mean? That means I'm not breathing enough to push the carbon dioxide out. So if I am exercising and I am really, my breathing rate is high, but if you measure the carbon dioxide produced or in the alveoli, that is 40, let's say 40 millimeter. Why is that? I am producing more carbon dioxide, but I'm ventilating higher as well, so I'm moving it out as well. So the alveolar carbon dioxide is 40. Will you call me hyperventilating or not? No. By definition, chemical definition, hyperventilation is if I wash out more than, bring the carbon dioxide lesser than 35. And by definition, hypoventilation is when I bring the carbon dioxide level above 45 in the alveoli. So keep that in mind. Now, what are the factors that are affecting the oxygen? So look, we had that equation over here as well. What is that equation? We saw atmospheric minus pH2O plus inward fraction of inward oxygen pressure minus this PaCO2 over R. That is the formula for oxygen. These are the factors that affect it as well. For example, atmosphere. That is one factor. If you go to higher altitude where the pressure is low, then automatically PaO2 here will become low. On the other hand, if you put someone in the hyperbaric chamber where the oxygen levels are, pressures are double, then the PaO2 will become double as well. So that is one factor. How about the fraction of oxygen given? That also is, if you increase the fraction of oxygen given, for example, how can you do that? By giving oxygen supplement. If you give oxygen supplement, so as you increase the concentration of the oxygen, percentage of oxygen, pressure of oxygen will go up. No big deal. So that is the second factor. Just remember this formula and you have the factors. Third one is carbon dioxide. So if the carbon dioxide, remember we talked about it over here, carbon dioxide production is related to oxygen consumption. So if the respiratory exchange ratio is 1, that means for 1 carbon dioxide produced there is 1 oxygen needed, then can I say that if you are hyperventilating, you move the carbon dioxide out quickly, then who would take the rest of the space? Oxygen, right? You have to make a 760 over here. Or if you start accumulating carbon dioxide here by hypoventilating, then carbon dioxide would exert more pressure and oxygen pressure would reduce. So that is the third factor. Hyperventilating would increase PaO2 because it would reduce PaCO2. Hypoventilating will retain carbon dioxide, PaCO2 will increase, and of course PaO2 would reduce.